Welcome to the Deep Dive, where we take your source material and distill it into pure, actionable insight. Today we're plunging into the fascinating and sometimes perilous world of JavaScript.
Definitely fascinating, sometimes perilous.
Yeah. It's a language so many of us use, right?
Hmm.
From quick scripts to massive applications. But, few truly master it for building large, robust systems.
That's the challenge.
You might be using it for a simple input field. Or maybe you're building an entire single-page application. Either way, you've probably heard it called a wild child. Fun, incredibly versatile, but maybe with a streak of unpredictability.
And that reputation, for better or worse, it's kind of well earned. Our mission today is to unearth why that wild child reputation sticks, and maybe more importantly, how top developers are actually taming it. Transforming it into a reliable powerhouse for mission-critical software.
Right, how do you get that reliability? And to guide us, we're pulling some serious insights from Reliable JavaScript, how to code safely in the world's most dangerous language.
Great resource.
Yeah, it looks fantastic. It will promise us to cut through a lot of the noise, helping us understand not just what JavaScript can do, but maybe what it should do to build truly resilient applications.
Yeah.
Okay, let's unpack how we got here. JavaScript started its life as, well, what our sources describe as a dilettante.
A dilettante, yeah. I like that term.
Think about those early web days. It was kind of a part-time tinkerer doing simple tasks like validating a form field or, making an image swap on hover.
Basic stuff.
Exactly. If you accidentally declared a global variable back then, it was mostly a shrug and a no harm, no foul situation, right?
Pretty much.
Yeah.
What's truly fascinating, though, is how quickly that landscape shifted. It demanded so much more from JavaScript, almost overnight, it feels like.
Yeah.
Well, with the advent of technologies like iframes and XML HTTP, the precursor to modern asynchronous requests back in the late 90s, and then Google making Ajax a household name with Gmail in 2004 and Google Maps in 2005.
Oh, yeah, that changed everything.
Right. The browser wasn't just a document viewer anymore. It became a powerful application platform. Suddenly, JavaScript had to shoulder much heavier burdens, rapidly evolving into the backbone of complex single-page applications, SPAs, and even server-side stuff with Node.js.
Wow. So it went from page scripting to full-blown application development.
Seemingly overnight, yeah. It was a huge leap.
And this rapid, almost unexpected growth really exposed some deep-seated quirks, didn't it?
Oh, absolutely.
For example, unlike compiled languages like C# or Java, there's no strict compiler to catch simple errors before your code even runs.
That's a big one.
A typo in a variable name or a call to a non-existent function can literally lurk in your codebase for months, completely undetected.
Waiting to bite you.
Until a specific, rare user interaction triggers that exact line of code, leading to a sudden, inexplicable crash for your users. It's like having a ticking time bomb.
It absolutely is. And this raises a crucial question. How do you navigate JavaScript's famously flexible, sometimes ambiguous approach to things like equality and truth?
Oh, yeah, the double equals versus triple equals.
Exactly. We're talking about the difference between for equality with type coercion versus for strict equality, or those truthy and falsy values, where even 0 or an empty string is considered falsy.
Right.
These behaviors can be charming, maybe even efficient in small scripts, but in large mission-critical systems, they can be maddening sources of subtle bugs. I remember a project where an empty string from an API response being falsy led to a critical section of code being skipped entirely, caused a complete UI malfunction, took ages to trace.
Ouch. And the ease with which you can unintentionally break existing code. Imagine refactoring a simple property name like .myProperty. You might think a global search and replace is enough.
You'd hope so.
But JavaScript reminds you, not so fast, you forgot to search for my property.
Right, the bracket notation.
Or even worse, dynamic access like my object prop, where prop holds the string my property.
Yeah, good luck finding that easily.
Our sources point out that this kind of implicit dependency makes code incredibly brittle and prone to subtle, hard-to-find errors during maintenance, especially in a large code base.
Brittle is definitely the right word. It's a find and replace nightmare, basically.
So historically, choosing JavaScript for an enterprise-level project wasn't considered the safe bet like C# or Java.
Not at all. Its reputation for making it all too easy to write disastrous code was, unfortunately, pretty well earned back then.
But things have changed.
Well, the language has just become too powerful to ignore. Think Node.js for scalable, real-time applications, or client-side frameworks like Angular and React for building rich user interfaces. Its strengths are undeniable now.
So you can't just avoid it.
Exactly. The key then is to acknowledge these inherent risks and, more importantly, to proactively mitigate them. You need an engineering mindset.
That's the pivot point, isn't it? If JavaScript is this powerful but quirky language, how do we make it reliably behave? Our sources strongly suggest we need to adopt that engineering mindset, borrowing heavily from more staid, maybe traditional programming languages.
Bring some order to the wild, yeah.
It's about bringing order to the wild.
Absolutely. This means applying time-tested principles like design patterns, comprehensive unit testing, and crucially, test-driven development, or TDD.
TDD.
TDD, in particular, is transformative, especially for JavaScript. It is that familiar red-green refactor cycle. You write a failing test.
The red part.
Right. Then you write just enough code to make it pass.
Green.
Green. And then you clean up and refactor that code. This iterative process isn't just about building quality. It's about building reliability in from the ground up, one small, verified step at a time.
I know the conventional wisdom is test first. But for many developers, myself included sometimes, it still feels backward. Beyond the textbook reasons, what's the real practical difference TDD makes for JavaScript developers wrestling with complex systems, especially when deadlines are tight and you just want to get the feature out?
That's a great question, and it really highlights TDD's unique value in JavaScript. Because JavaScript lacks that compile time safety net we talked about, TDD effectively becomes your early warning system.
Ah, okay. Like a substitute compiler.
In a way, yeah. If you write the test after the code and it passes, how do you truly know it's passing because the code is correct? It might be passing just because the test itself is faulty, or it simply validates existing, maybe incorrect behavior.
Right, you might have written a bad test.
Exactly. Writing the test first ensures it validates expected behavior. It forces you to design for testability from the outset, which almost always leads to cleaner, more modular designs.
So it improves the design too.
Definitely. It's your personal compiler pushing you towards clarity and making your code less brittle. It's worth the initial effort.
And what about those big picture principles we hear about in other languages, like solid and DRY? Are they still relevant here, or does JavaScript's flexibility kind of let us off the hook?
Oh, they're absolutely central, maybe even more vital in JavaScript because of its inherent flexibility.
More vital. How so?
Well, take the single responsibility principle, SRP, that a module should have only one reason to change. D3JS's SVG line function is a perfect example from the source. Its sole responsibility is to produce an SVG path from data. That's it. Everything about how it does that is external and configurable. This means the core function itself is incredibly stable.
Okay, focused.
Then the open-close principle, OCP, encourages extending existing working code rather than modifying it. That's how you build adaptable systems without introducing new bugs every time you add a feature.
Right, extend, don't modify.
And the DRY principle, don't repeat yourself, is paramount. Why? Because without a compiler catching certain classes of mistakes, repeated code in JavaScript means repeated opportunities for subtle errors to go unnoticed until they hit your users.
Ah, because a mistake in one place is now a mistake in many places.
Precisely. Every time you duplicate logic, you double or triple the surface area for unexpected behavior and bugs.
Okay, so TDD and these foundational principles sound like a phenomenal starting point. But what tools and specific techniques can help us keep our JavaScript reliable day-to-day, like when we're actually writing code?
First and foremost, linters are indispensable. Tools like JShint, ESLint.
Yeah, I use ESLint.
They act as your compiler light. They identify syntax errors, style violations, questionable constructs before your code even runs. This catches a whole class of mistakes that JavaScript's interpreted nature would otherwise miss, saving you from those lurking for months bugs we talked about.
That makes a lot of sense.
Wow.
Linters is a kind of static guardrail. But are there common pitfalls? Like, can you overuse linters, make them too strict?
Absolutely. It's definitely a balance. An overly strict linter configuration can lead to linter fatigue,
Right.
where developers just start ignoring warnings because there are too many.
Yeah, noise.
Exactly. The key is to configure it to catch genuine errors and enforce agreed-upon team style, not to micromanage every single line. It should be a helpful assistant, not a dictator.
Okay.
But on the topic of managing complexity, if you're building larger systems with many objects needing to talk to each other, managing those connections and how they get created, that can become an absolute nightmare.
Oh yeah, dependency spaghetti.
Precisely. We've seen patterns like modules and factories, but our sources point to dependency injection, DI, as a key solution here.
How does DI really cut through that complexity? Are there trade-offs?
DI is huge for reliability and testability. Instead of an object creating its own dependencies, like fetching data or talking to another service, those dependencies are injected from the outside, usually during setup.
So you pass them in, basically.
You pass them in, yeah. This significantly boosts testability because you can easily swap in fake objects like spies or mocks during testing. You gain fine-grained control over how your code behaves. You can even simulate rare error conditions that might be really difficult to reproduce otherwise.
Ah, okay, so testing gets much easier. What's the trade-off?
The trade-off is often a bit more upfront configuration, maybe using a DI container or a slightly more complex code-based structure initially, but the gains in testability and maintainability down the road. Usually well worth it for anything non-trivial.
Got it.
Yeah.
Moving to a different kind of architectural challenge, I've heard about cross-cutting concerns, things like caching or logging that seem to infect every part of an
Yeah,
application.
they pop up everywhere.
They make the core logic messy and hard to maintain. How do you keep that under control without just copy-pasting logging code all over the place?
That's where aspect-oriented programming, or AOP, comes in. It's a bit more advanced, maybe.
AOP. Okay.
And an AOP framework, like ALP.js mentioned in the source, lets you wrap functions with advice.
Advice.
Think of advice as small, modular pieces of code that can run before, after, or around your core logic without modifying the original function.
Interesting. Like middleware?
Sort of, yeah, but applied more broadly. For instance, you could add caching logic to a function like getRestaurants The AOP framework intercepts the call, checks the cache, and only calls the real function if needed. The beauty is, the getRestaurants function itself doesn't change. It doesn't even know about the caching.
Ah, so it keeps the core logic clean.
Exactly. It keeps your business logic clean, cohesive, and adheres perfectly to that open-closed principle we discussed. You extend functionality without altering working code. It's a very elegant way to manage these common yet intrusive concerns.
So JavaScript has its own unique way of doing things, which can be that double-edged sword. Incredibly flexible, but also a source of confusion. How do we embrace its idiomatic features while ensuring reliability and avoiding those classic JS gotchas?
Well, one fundamental aspect you really have to grasp is that functions in JavaScript are first-class objects.
Right, you can pass them around like variables.
Exactly. They can be passed as arguments, returned from other functions, and even have their own properties and methods, just like any other object. This flexibility, combined with nested functions, allows you to create truly private variables and functions, effectively hiding internal implementation details from the outside world.
Encapsulation, basically.
Precisely. The conference.simplecache module from our source is a great example. It uses a private variable inside a function scope to store the cache, while only exposing specific functions to interact with it. Creates a clear, reliable interface.
Okay. And then there's that this keyword. It often confuses developers, leads to completely unexpected behavior, especially when functions are passed around or used in different contexts.
Oh, yeah.
It feels like a constant source of, why is this happening? Moments for people learning JS.
For good reason. This is probably responsible for more head-scratching moments in JavaScript than any other single feature.
So how do you tame it?
Understanding call, apply, and bind is absolutely essential. These are methods available on all functions. They allow you to explicitly control what this refers to when a function is executed, preventing many, many common bugs.
Can you give an example?
Sure. Our sources give a great one. Creating a polyfill for array.prototype.forEach. For older browsers. Inside the polyfill, you use call when invoking the user's callback function. That ensures the this context is set correctly, just like the native for each would do. It gives you precise control over one of JavaScript's most volatile features.
Got it. Control the context. Now, since JavaScript is a type-free language, how do you ensure objects play by the rules? When there are no explicit interfaces like in Java or C#, it sometimes feels like the Wild West where anything goes.
Yeah, you don't have that compiler check saying, hey, this object doesn't implement the iUser service interface.
Right.
But we can implement the spirit of interfaces through something like a contract registry, as described in the source.
A contract registry?
Yeah, it's a pattern. This module allows you to define explicit expectations, contracts, for what arguments a function expects and maybe what shape an object's return value should have.
So you define the rules yourself.
Exactly. You can even attach these contract checks as aspects using AOP, so they run only during testing. This gives you powerful validation during development without impacting production performance with extra checks.
That's clever. Testing only.
And this also ties into duck typing, which is a very JavaScript-y philosophy.
If it walks like a duck.
And quacks like a duck, it's probably a duck, or at least good enough to be treated as one for this purpose. In code, this means you check for the presence of necessary properties or methods, like does this object have an X property as
Yeah.
X and something, rather than relying on strict explicit type declarations. It allows for more flexible yet still predictable code. You check for capabilities, not type identity.
Okay, check for what you need, not what it is. Makes sense. This all sounds great for the back end and the internal logic, but how does this apply to what the user actually experiences, like the UI? That's often the most visible part when things go wrong.
Right, the front end. When testing UI, the first rule is somewhat counterintuitive. Try to avoid it.
Avoid testing the UI. How does that work?
Well, what it means is encapsulate as much of your UI logic as possible into functions that have no direct DOM interaction. Pure functions, ideally.
Ah, separate the logic from the rendering.
Exactly. Then your unit test can focus on verifying that the correct logic functions are called when, say, an element is clicked, rather than testing brittle visual appearance details like, is this button blue?
Okay, test the logic behind the UI.
Then, for actual UI testing, integration tests maybe, focus on functionality. Is the correct event handler executed when this element is clicked? Is an element hidden when it should be based on the state? Pixel-perfect visual checks tend to be incredibly fragile. They break with every tiny design tweak, giving you false negatives and just wasting development time. Focus on behavior.
Got it. Behavior over appearance for tests. And what about when the application just feels sluggish or unresponsive? How do we find the bottleneck without just guessing where the slowdown is happening?
Browser profilers are your best friend here. Chrome's DevTools, Firefox's tools, they're invaluable.
The Profiler tab.
Yeah. They show you exactly where your application is spending its time, millisecond by millisecond. They give you the hard data you need, not just hunches.
What's a common thing people find?
A common aha moment we see in JavaScript projects, often highlighted in our sources, is realizing that direct DOM access reading or writing to the page, especially within loops or frequent re-renders in frameworks.
Ah, touching the DOM too much.
Exactly. That can be a far bigger performance bottleneck than even complex calculations. It's often counterintuitive. People optimize the math, but the DOM interaction is the real killer.
Because the browser has to repaint and reflow.
All that expensive stuff, yeah. It's a prime example of how JavaScript's single-threaded nature and its interaction with the rendering engine demand careful profiling. Minimizing those DOM updates, maybe by batching them or being smarter about updates, can dramatically improve user experience and responsiveness, often with surprisingly little code change once you know where to look.
Okay, profile first, then optimize the bottlenecks, especially DOM stuff. We've taken quite a deep dive today into why JavaScript earned its reputation as a wild child, but also how modern software engineering principles and tools are really transforming it.
Yeah, making it into a reliable powerhouse, even for the most demanding applications.
Feels like it's grown up a lot.
It really has. It's clear that JavaScript's incredible flexibility is its greatest strength, but it absolutely demands discipline to harness effectively. You can't just sling code anywhere, not for serious projects. By embracing things like TDD, leveraging powerful tools like linters and dependency injection, really mastering its unique features like this binding, and maybe even creating your own contracts for expected behavior, you absolutely can build applications that are not only powerful but robust and remarkably reliable.
So what does this all mean for you listening? In a language that offers so much freedom, so many ways to accomplish any given task, the question isn't just whether you can do something in JavaScript, but maybe whether you should. How will you choose to apply discipline to JavaScript's extraordinary flexibility in your next project to turn its wildness into true, reliable power?